Okay, so to start up, we have to change this dataset since, as you can see, it's not currently usable for filament tracing since it's Golgi-cox staining. So what we will do first is resize this dataset to resample it by using 512 by 512 and half the number of slices, since this is enough and it will greatly speed up the calculations. So the next step is to check the image properties here and adjust the Z calibration, since here it looks a bit more accurate to me, but this can always be changed back later on. So now you can make sure that if you have the extensions license, have the Fiji application correctly set and send the image to Fiji here. So this takes a few minutes. Don't worry, sometimes the image displays quite fast, but the interface of Fiji takes a bit more time. So you just have to be patient, but you should finally see the full Fiji object. So as you can see here, we just have the window. So this is how the dataset looks like, but we don't have the Fiji interface. So okay, so now it took a few minutes, but we finally got the interface. So we don't need the update. What we need is to just go edit, invert, and invert the values here. And then it looks more like a fluorescence image. And additionally, you can do a bit of background subtraction to clean up a bit this dataset. So we go to Process, Subtract Background here. And for this dataset, I made sure that I used sliding paraboloids and rolling board radius of 50 pixels. Looked okay to me. You have to process all the slices, and now it really looks usable for Imaris to do some filament tracing. So now you just have to send this image using the plugin back to Imaris, image to Imaris, and now you can close Fiji. And now you have the dataset that we will use here for filament tracing. Okay, so the next step now is to define the filament object, and in this case, since the dataset is it's not noisy per se, but we have several small structures here that might mess up the automatic detection, plus it's quite dense here. So I think a semi-manual approach is more recommended in this case. So what we will do here, we can create somas as a starting point by using surfaces objects and then import them into filaments, or we can start directly with a filament object and then just select the somas that we want to use and draw manually the dendrites afterwards. So let's do this version here. So I start with a filament object here. We want to calculate the soma model, and We don't need here currently the slicer view. Let's proceed to the next step. So we have to detect the starting points, so the dendrite beginning and the largest and the thinnest diameters. Again, we can go to slice here, the slice view, and get an idea of the diameters. So you have the read here, so this is 3 microns currently. If you take the largest, it's about 10 microns. Let me slide down here. If we go maybe just here again, well, 11 microns, something like this for the largest. And regarding the dendrites, I would say, let's zoom in here to be a bit more precise. 0.7, 0.6 or 0.7, I would say. So I'll go back to 3D view. Let's put 1.6 here and something like 10 microns. So now we have the big blue spheres, which are the starting points, which will be our somas. So we want to keep only a few of them. And in this case, I think it might be interesting to get this one, and the one that's here. So in order to do that, I have to increase the threshold like this. And then regarding the dendrites, I want to make sure that I don't have spots everywhere, but I get, I think here, this. Currently it doesn't matter since we will not use it, but just for the sake of the demonstration, usually you want to set this up not that high, and then you can always make sure to remove disconnected segments, and you can always refine this afterwards. Here I just want to go to the next step, which is the one that interests us the most, which is the soma creation. And I think this looks pretty good to me. So let's just finish right there. Without any other considerations, since we just want to keep those somas here and use them as a starting point. So we'll have to wait a bit. Okay, so this is the automatic detection, and we don't really care about this anymore. Anyway, here we can select individual somas. So if I control click, I have selected now these two objects here. And in the edit tool, you can duplicate the selection. If you do that, you get a new filament object here with the soma. So here it seems it didn't do the job properly. So let's just try it again. So if I go back to my filaments here, I want to select the point and not the segment. This should get the job done. If I select this point and this one, for instance, or let's say this one, those two here. Now duplicate, and now we have two nice somas, and you can work from there, from a clean start. So now let's start with this manual drawing. So we have to select an object here in the edit mode. Now I can go to the draw mode here and select this object as the starting point, And now when I want to draw, I can see a line here that will continue and follow the signal. So I can keep my left mouse button pressed to rotate here the data set to have an idea of what is going on, and then I can draw, and once I'm satisfied I can shift and left click to validate. Now if I want to continue here, I will make sure that I select this segment here and select this as a starting point. So now instead of starting from the soma, I will start from this branch, and I can draw a new one. So for instance, I will go here this way, and when it starts to disappear, you have just to go back a bit, shift, and so on. So select this as a starting point, and from there I can draw the next branch, and so on. I can go back here to select again this branch, should be probably this one here. Set a starting point and draw something like this. And from there I can probably draw this branch here, and then we have more. So we have one here, and I will use this one as a starting point to diverge from here. So here it doesn't look to work properly, so I will just make sure I get the start correct and continue it like this. Okay. So I won't do all the branches, of course. So when this starts here, and you have done the tree properly, what you can do now is detect the spines, for instance. So you can go to the creation wizard here, and you can recalculate the dendrite diameters and then the spines. So here, this is what we will do. I can recompute the dendrite diameters, so you just have to make sure the threshold here covers your signal. Okay, looks okay to me. And then you can proceed with detect to detect the spines. So again, here you have to make sure the seed points and maximum length is set correctly. So for this, you can go back to the slice view, and if we're interested, let's say in this region here, let's say this distance is approximately 2 microns. So this is probably the tallest spine that you want to measure. What would be the spine diameter? 0.6 again. So let's go back here. Let's put something like this, 0.4, and the maximum length 2. So we will get some thresholds again, and we want to avoid the big too large a number here, and just make sure that our spines are properly detected. Looks probably okay, but you have to make sure that this corresponds to your settings. So let's proceed. Again, take some time to do the calculation probably. Okay, so similar to the dendrite diameter, we have to calculate the dendrite, the spine's diameter. Can be quite tricky, but I think something like this looks okay, and then we can finish. So obviously you will have to adjust here the settings to get the correct value, but then if you are interested in getting some statistics, you can go here to the statistics tab, and you will have detailed statistics about any kind of objects. So here, if you are interested in spines only, we can just keep the spines checked, and so here only the statistics regarding the spines will be displayed. If you want to make sure that you have everything available, you can click here on the small wedge here to see, for instance, here if you have all the statistics objects checked, everything that is needed. For instance, I don't know if you're interested in the spine neck volume, for instance, or the spine neck length, make sure it's checked. So it will be recalculated, and now it should be available in this list here, so spine neck length, for instance. And finally, you can color the objects, let's say the spines, based on those statistics and the type of statistics you want. So spine length like this. And the dendrites, I want just the base color here. So now I can easily identify the objects and see a visual representation of their different characteristics. Okay, so that's it for today's video. Thank you for watching. Bye bye.